When using the method of initial rates, we have to start by setting down a general rate law. So the general rate law for this reaction would be that the rate was equal to K, the rate constant, times the molarity of the two reactants, NO and O2, each raised to the power of their order. So we'll choose X for NO and Y for O2. We also have to hope that one of the reactant concentrations has been changed in a purposeful way in order that we might discover the order with respect to that reactant. So we'll notice from experiment 1 to experiment 2, the concentration of O2 has tripled. In other words, the concentration of O2 in the second experiment is equal to 3 times the concentration of O2 in the first experiment. And we will use this in order to discover the order with respect to O2, or the value of Y. It's also important to note that in the same two experiments, 1 and 2, the concentration of NO was kept constant. So now we're going to look at the rate law for each of the two experiments, experiment 1 and experiment 2. So the rate law for experiment 1 would be equal to K times the NO concentration from experiment 1 raised to the power X times the concentration of O2 from experiment 1 raised to the power Y. We can write an analogous rate expression for the second experiment. The rate in the second experiment will be equal to the same K times the concentration of NO from the second experiment raised to the power X times the concentration of O2 from the second experiment raised to the power Y. What we're going to look at now is the proportion of rate 1 to rate 2, or the ratio of rate 1 over rate 2. So we'll divide rate 1 over rate 2, or we'll divide the rate laws. Again, we take the first rate law for experiment 1. It's equal to K times the NO concentration from experiment 1 raised to the power X times the concentration of O2 from experiment 1 raised to the power Y. In the denominator, though, we're going to try to simplify things. So we'll have the same K. We'll have the NO concentration from experiment 1, since from experiment 1 to experiment 2 those are equal, and we'll substitute for the concentration of O2 in experiment 2, we'll substitute 3 times the concentration of O2 from experiment 1. That will be raised to the power Y. Now we look at what cancels. The NO molarity from experiment 1 cancels, the K's cancel, the O2 molarity from experiment 1 cancels. We're left with a factor of 1 over 3. So we have 1 to the power Y divided by 3 to the power Y. Now we take the values for the actual rates, and we take the ratio of those. So the rate from experiment 1 divided by the rate from experiment 2. And what we come up with when we punch that into the calculator is a value of 1 over 3. This means that the value of Y must be equal to 1. Now we're going to do the same thing to discover X, the order with respect to NO. And we're going to do this by comparing the data in experiment 2 to the data in experiment 3. And that's because from experiment 2 to 3, the molarity of O2 stays constant, but the molarity of NO is doubled. So the rate law for experiment 2 is given by K times NO from experiment 2 raised to the power X times O2 from experiment 2 raised to the power Y. We can write the analogous rate law for experiment 3. That's equal to the same K times the concentration of NO from the third experiment raised to the power X times the concentration of O2 from the third experiment raised to the power Y. If we take the ratio of these two rates, so the ratio of the two rate laws, then we come up with on the top again K times the NO concentration from experiment 2 raised to the power X times the O2 concentration from experiment 2 raised to the power Y. But in the denominator, we want to simplify things. So instead of the NO concentration from experiment 3, we will write 2 times the concentration of NO from experiment 2. We will raise that all to the power X. And the O2 concentration from 2 to 3 is unchanged, so we'll write the O2 concentration from experiment 2 raised to the power Y. Now look what cancels. We can first cancel out the K. Oh look, I forgot the K in the denominator, so pop that K in. And then once it's in, we'll cross it out. We'll also cancel the NO concentration from experiment 2 We'll cancel the O2 concentration from experiment 2, and we're left with a factor of 1 over 2, 1 raised to the power x and 2 raised to the power x. Now we put in the values of the rates for experiment 2 and experiment 3. And once we calculate that ratio of the rates, then we will have our ratio. We find that that is equal to 1 over 4, and therefore x must be equal to 2. The next task is to discover the order and the rate constant of the reaction. The order is simply the sum of the order with respect to each reactant. So we can write out the rate law, which we have discovered, and that is that the rate is equal to K times the NO concentration squared times the O2 concentration. So the order is equal to 1, which is the order with respect to O2, plus 2, which is the order with respect to NO. So we add these up to get 3, which is the overall order of the reaction. For K, we can take any one of the 3 experiments and find K by rearranging the rate law so that K is isolated. So K is equal to the rate, let's say, of the first experiment divided by the NO concentration squared from the first experiment and the O2 concentration from the first experiment. So we put those numbers from the data table into this equation. We have the rate on the top, and we hang on for dear life to those units because you know your teacher is going to be interested in the units. We divide the rate by the NO concentration squared. Again, we square those units as well, and the O2 concentration. Once you plug that into your calculator, you get a value for which you will have 2 significant figures, since all the data in your table has 2 significant figures, and when the dust settles, the units of this are liters over moles squared divided by seconds.